Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today in this lecture we will discuss that what does mean by Kirchhoff's current law. Before going into in-depth intuition of the KCL, Kirchhoff's current law, I am going to discuss that why this Kirchhoff's law comes into picture if there is already Ohm law present. So the answer is that the Ohm law is only valid for a simple circuit. So here we have the simple circuit consists of only one battery and only one resistor. So in this case, this voltage, current and R will be come from the formula of the Ohm law, which is equal to R is equal to V by I, V is equal to I is equal to V by R. So these parameters comes from the law, Ohm's law. Now, if there are large number of voltages are connected in parallel or in series with the large number of the resistors, so a complex a circuit will be formed. At that complex circuit, the Ohm law still valid, but if you apply the Ohm law at each and every junction of that large complex circuit, then the mathematics will be more complex. So for the simplicity, the scientist whose names Kirchhoff's, who present the law which is called Kirchhoff's laws, and that laws, one is for the Kirchhoff's current law and the other one for the Kirchhoff's voltage law. So in this video we will discuss only the Kirchhoff's current law and what is that law which is presented by Kirchhoff. So before going into the in-depth intuition of the KCL, we'll have to consider a simple pipe. So here this is the pipe for the analogy, and inside this pipe the water is flowing. So if it reach here, here will be junction, and at this junction this pipe will be attached to two other pipes. So when the water flowing in this pipe in this direction, and if it reach here to the junction, that water will be separate. Some of the water will go in this pipe and some of them will be flow in this pipe. The amount of the water in the pipe depend upon the diameter of the pipe. So here the diameter is less, therefore less current, so therefore less water will be flow in this pipe as compared to this pipe. The same analogy is for the current as well. So here if these are the wires, so this is the wire which is connected to the other wire through this junction. The current in this wire go toward this junction will be equal to the sum of these two currents. So this is that diagram. So here the current enter toward this junction, this is the current. Here at this junction, that current will be divided into I1 and I2, and the magnitude of that current will depend upon the diameter of the what we can say the diameter of the wires and also the resistor attached to that, but we will discuss that in more detail in this video. According to Kirchhoff's law statement of the Kirchhoff's law is this. The current entering the junction, the current toward this junction is equal to the current leaving this junction, is equal to the current leaving the junction. So this is the statement of the Kirchhoff's current law. So in this case the current entering to the circuit is I. So this is the I, which is equal to the current leaving this circuit is actually I1 plus I2. So this is the Kirchhoff's current law. In order to rearrange, so here rearrange this, I is equal to minus, so I minus I1 minus I2 is equal to 0. So from here we can state the Kirchhoff's law is the sum of the all currents entering the junction and leaving the junction will be equal to 0. This is the second statement of this Kirchhoff's current law. And it means that the sum of the all, so here I am going to change the color, the sum of the all currents entering or leaving, entering and leaving the junction will be equal to 0. And this is the third statement for that Kirchhoff's law. These three statements are same. So here the statement of the Kirchhoff law is the current entering to the junction will be equal to the current leaving the junction. So this is that. Now we will apply the KCL, Kirchhoff's current law, in this in this complex circuit. So in this complex circuit we have the 6-volt battery, which is and 3 resistors are connected in parallel with this battery. Let's consider the 20 ampere current is flowing in this direction. So here at this junction, according to KCL, Kirchhoff's current law, the current entering to this junction will be equal to the current leaving this junction. So here the current leaving the junction, here at this junction, this current will be divided, let's say it divided into 8 ampere here, and the remaining 4 ampere, sorry, the remaining 12 amperes are moving in this direction. Okay, and this 8 ampere ahead at this junction will be divided into let's say 2 ampere and 6 ampere. So the Kirchhoff's law now applied at this junction. According to the Kirchhoff's current law, the current entering this junction, which is 8, will be equal to the current leaving this junction, which is also 8. 6 plus 2 is 8. And this 2 ampere current now again move in this wire. So here this is the 2 ampere current. Now toward this junction, from this side the 2 ampere current, and from this side we have the 6 ampere current. And now at this junction, according to Kirchhoff's current law, the currents entering the junction will be equal to the current leaving the junction. So here the current entering is 6 plus 2 is 8, will be equal to the current leaving the junction. So here it will be the 8 ampere. Now the 8 ampere current is moving toward this junction, and from this side the 12 ampere current is coming, and according to Kirchhoff's current law, the currents entering this junction will be equal to leaving. So the current entering in this case is 8 ampere plus 12 ampere is equal to 20 ampere, and now this will be 20 ampere, and at that same current again come toward this voltage. So this was the practical implementation of the Kirchhoff's current law. So Kirchhoff's current law only in this case focus on these junctions, So he explored these junctions and the current distribution at this junction. In this case, I roughly write 8 ampere and 12 ampere. So this distribution of the different distribution of the currents will be depend upon the diameter of the current, the diameter of the wire, and also depend upon the resistance, the combination of resistance in parallel or in series. So this was the Kirchhoff's current law. Now the last point I am going to explain is that this KCL, Kirchhoff's current law, is also called law of conservation of charges, law of conservation of charges. So how to justify this so according to KCL, so here from here the current entering the junction is equal to the current leaving the junction, and we know that the formula of the current I is equal to charge per unit time. So here from this we can write that this equation, let's say this is equation 1, the equation A now implies that this is I, so Q by T is equal to, this is I1, so Q1 by T1, sorry, Q1 by T, and this is T2, Q2 by, so this is I2, which is equal to Q2 by T. Now taking 1 over T common from both sides of the equation, so this is 1 over T into Q, which is equal to 1 over T into Q1 plus Q2, and this become Q is equal to Q1 plus Q2, because this 1 over T is cancelled with this 1 over T, and this is the this is called the law of conservation of charges. It means that the number of charges entering the junction will be equal to the number of charges leaving the junction. So this is called law of conservation of charges. So therefore KCL, Kirchhoff current law, is called the law of conservation of charges. And this was the simplest explanation of the Kirchhoff's current law. This is the practical implementation. This is the analogy for this Kirchhoff current law, and this is the background for this Kirchhoff current law. And similarly, this is the statement of this Kirchhoff law, and Kirchhoff's law is also called law of conservation of charges, and this is the justification of this, that how Kirchhoff's law is called, Kirchhoff current law is called the law of conservation of charges. So that's it guys, thanks for watching.